All right, this is physics video 5.02. Looking at using Newton's law with one-dimensional problems, the correlating homework would be 5.04. So our videos and our homework assignments don't necessarily match up in this chapter. So we're going to look at what happens. How do we evaluate net force, directions, and we're going to start off with looking at how the normal force can change. You might be thinking, well, I thought the normal force was fixed. And no, it's not. It depends on the other forces that are involved. So let's take a look at that with question number 4. A friend has given you a gift that has a mass of 10 kilograms. The box is resting on a smooth, frictionless table. Determine normal force. For all of these next two problems, we're going to take up to be the positive direction, and they're in the vertical only, so I'm not going to worry about a horizontal coordinate. So let's do part A. Give myself a box. I made myself a little template because I want to make sure these vectors are correct. So if I'm sitting on the table and I'm not moving, I'm going to have a normal force, and I'm going to have a weight vector. I'm going to have gravity, the force of gravity, which we call weight because that's mass times acceleration due to gravity. So here's my little template. Remember, the forces start from the middle of the box. They act upon the middle of the box. Okay, so that's my weight vector. A couple of things to point out. First of all, if you look in other textbooks, well, in which I draw the normal force, is this weight vector going to change no matter what we do to the box? The answer is no. The weight vector is always going to be the same unless I change the mass of the box or the elevation, which isn't very likely. Sometimes we do change mass, and in that case, the weight vector would change. All right, so my motion analysis is I have none. There is no motion, so I do a little green X. That means that my normal force has to be equal and opposite. Now, sometimes you'll see normal force, if it's setting on a table, so that's my horizontal surface, you'll see the normal force drawn from the point of contact. Usually, and to the best of my knowledge, AP says it's okay to draw the force from the point at which it originates. So we have two vectors that are equal and opposite, my normal force and my weight vector. All right, I should have done the normal force in blue. I'll color code these after this. Oh, so they say determine the normal force. Oh, I skipped a whole step here. All right, so let's, for all of these, let's make acceleration due to G to 10. Let's just round it. We're gonna make it 10. So here I have a 10 kilogram box. So this is gonna be 10 times 10. So I'm gonna have a negative 100 Newton force this way, which means this is gonna have to be positive 100 Newtons. All right, let's move on to letter B. Draw my box again. And we just said the weight vector can't change. The weight vector doesn't change, so it has to be same length. And we know that's going to be negative 100 Newtons, because we calculated it the last time. But this time, your buddy's pushing down with a force of 40 Newtons. So he's pushing down on the box. And if this is 100, that would be half. So we want to go to about right there. So we have an applied force of negative 40 Newtons. Well, I still have to do a motion analysis. Is the box moving? I have no motion. So what does that mean for my normal force? What is the implication here? Well, the implication is that if it's not moving, my downward forces and my upward forces have to be equal and opposite. So that means that this upward force has to be, I'm going to go into my writing here. That means that my normal force now has to be 140 Newtons because my forces have to be balanced. Because I don't have motion, F net has to equal 0. So by pushing down, I increased my normal force. And that makes sense because think about it. If you push down on a box and the table's not capable of exerting a greater upward force, you'll break the table. So if it was a real flimsy table, you would crack it. Okay, so letter C says, now your friend pulls up on the box. Does my weight vector change? Folks, the weight vector cannot change unless you change the mass. You're going to have to get used to me saying that. I'm going to say that many, many times. So get my little template out here. But now your buddy is taking that applied force and it's going in the opposite direction. So we're going to do, and that's about a positive 40. So notice I'm using this to scale. If this is 100, then 40 has to be a little less than half of that. My vectors here are to scale. Your vectors have to be to scale. Okay, what's my motion analysis? Am I moving? No, still not moving. So that means that these vectors, and I have a normal force to draw in yet, have to be equal and opposite. Well, that means if I've got a negative 100 this way and this is positive 40, I have to have another positive 60 coming up this way. But it all ties back to analyzing the forces in the motion, forces in the motion, forces in the motion. You can't just slap vectors on and expect to get correct analysis and correct answers. All right, so let's move on to problem number 5. A 65-kilogram woman descends in an elevator that briefly accelerates at 1.8 meters per second squared. I left something off here. This should say down. Like, I don't have enough information to solve this problem. What does the scale read and what is her weight? Well, before we get started, one of the things that you should know is that the scale readings are actually showing the normal force. So when you see a scale, and you're reading a scale, you're seeing the normal force. And that's going to give you either newtons or pounds, but that's not your mass. So if it asks for her weight, we're going to do this. If it asks for her mass, we'd have to divide it to get, divide it by 9.81, get her mass. Oh, it says both. Oh my golly. I have another typo. What does the scale read and what is her mass? So not the same thing. We're going to do both. All right, so let's start off with the free body diagram. We still have up as a positive. So let's use the same weight vector again. I'm going to keep my template. She is 65 kilograms, and we're going to keep that rounding to 10. So we're going to have a negative 650 Newton weight vector. But if we now look at the normal force, so she's standing on the scale. She's standing on the scale, and she's got a downward acceleration. So let's do my motion analysis here. We've got movement down, and we have negative 1.8 meters per second squared. This negative is huge. If this is my downward motion, my acceleration's got to have a negative value. So what does that imply? I'm off screen here. I have another vector to draw in yet. I have to draw in my normal force vector. I'm going to do it in blue. If I make those vectors equal and opposite, can I have that? Can I have this? No, I can't. In order to have downward acceleration, I have to have a greater downward force than I do an upward force. So when I draw in my normal force vector, it needs to be less. I'm not sure what that's going to be yet. Remember, the normal force is what we're going to see the scale reading. So that has to be smaller. Well, how small? We have to find that out. So let's solve for that. So I know that I have F net is equal to mass times acceleration. I have my mass and my acceleration, but I don't know what F net is. I don't know what my normal force is. I don't know what the scale is going to read. Well, F net's going to be the normal force plus the weight vector. So if I take Fn, and that's positive, minus 650, it's negative, equals 65 times, and we're going to round that to 10. Oops, sorry. I don't want to re-record this whole video. I knew it as said as I knew it as said as soon as I said it. 1.8. When I solve, I find out that the normal force says 533 newtons. So the scale is, if your scale can show kilograms, it's going to give it's set so that you normally have it assumes you're standing still. So the scale is going to read, if I take that and I divide that by 10 and I norm that down to mass, it's going to take that down to 53 kilograms. So this is what the scale is actually going to read. What's her mass? 65 kilograms. Mass is is considered to be not related to your acceleration. So our scale reading, now maybe you have a scale that actually reads newtons. I don't know. I don't know that I've ever seen one like that. But we're going to get an incorrect scale reading because I have downward acceleration. And I missed something on the algebra. That's a negative. I missed something important. I really should re-record this. I really don't want to. Are you guys okay if I just explain it? The way that I had it written, actually, it's not a bad life lesson here. So the way that I had it written, I forgot to put my negative sign into the equation. So let's say, let's look at these two different possibilities. So 65 times 1.8 is going to be, so here I had positive 1.7, here I have negative 117. Do you see why that negative sign mattered? If I didn't have that negative sign here, I get that F sub n is equal to 767, and that's just wrong. So all because of that guy right there. So in a sense, maybe it's not a bad idea that I didn't put that in as I was going, because it shows you how one negative sign can make such a huge difference. This is now saying that I haven't, what I did was if I put in positive 1.8, that was saying I had an upward acceleration. And this would be consistent. If I was accelerating upwards at 1.8, that's what my force vector would be, my normal force, what my scale would be. But my acceleration is down. So when I told you guys that you live and die by your coordinate system, I wasn't kidding. Now, part B says, what does the scale read when the elevator descends at a constant speed of 3 meters per second? So I'm going to loop up here because I'm kind of out of room. So I'm just going to kind of do a partition this off. Part B, my weight vector is not going to change. I'm going to just eyeball it this time. All right, and what is my motion analysis? So I'm now descending. But what did the problem say that changes everything? Constant speed. So I have no acceleration. Well, if I have no acceleration, that means my vectors need to be equal and opposite. And so this is going to be a negative, if this is negative 650, this has got to be positive 650. And the scale is going to read 65. So because I'm going at a constant speed, I'm going to be okay. All right, so that pretty much hits the high points for how we start to analyze our motion. So we're talking about it, we're doing this one-dimensionally. So in the next video, we'll start to add horizontal and vertical together. All right, thanks for watching. Have a good day.